So you're all here for stormwater harming our streams. Our speaker is Daniel Nidzgorski from King County. Um, Dr. Nidzgorski is an ecosystem ecologist who studies carbon, nitrogen, and phosphorus cycling, especially in urban and suburban landscapes where everyday actions and decisions affect our local water quality. He works for King County Natural Resources with a focus on lake and stream water quality, which includes public health projects as well as watershed management and stormwater linkages. He is also passionate about advancing equity and social justice in the sciences, mentoring students, and developing engaging, effective scientific communications. This session is being filmed. It'll go for about 15, 20 minutes, and then during the question and answer, there will not be filming. And here you go, Doctor.
So all of our activities in urban watersheds contribute a lot of pollutants and materials into the environment. Stormwater can pick them up and carry them into our local lakes and streams. Sessions today are exploring quite a range of these, and I'll be focusing specifically on metals. Metals are the basis of our industrialized society, but they can also be toxic for human health and aquatic life. And today I'm not going to be looking at actual stormwater, but at the receiving waters that stormwater flows into. When it enters a stream, mixes in, what does that look like? What are the concentrations we're seeing? Is that going to be harmful? The data that I'll be presenting come from a long-term stream monitoring program, King County, Washington. King County is here in Seattle up through the ridge line of the Cascades. And to look at the effects of stormwater on these streams, we sampled them during wet weather conditions, either during or immediately after a rainfall when storm flow was entering those streams. So with this data set, I'm going to be addressing 4 questions. First one that everyone wants to know about is toxicity. Are metals concentrations high enough that they might be harming aquatic life in the streams? Second is a comparison to baseflow metals concentrations. Okay, if we're seeing metals, are they actually coming from stormwater or not? Third is the trends over time, things getting better or worse. And lastly, I want to explore some pollutant sources. What can this data set tell us about where these metals might be coming from as a first step to helping then fix those? So these are our study sites, 33 sites scattered across western King County, the more lowland developed areas. You heard this morning's talk, you heard about really nice random stratified designs. This is not that. There's a lot of historical baggage into why these sites were chosen. They were part of King County's ongoing routine stream monitoring programs. They were then selected for this metals. Almost all of them are downstream near either the mouth of the stream where it enters the sound or the lakes, or where it enters a major river. Some of these sites in triangles are a secondary upstream site, kind of breaking the stream into 2 reaches. Today I'll be looking at the big picture overview, staying at this 30,000 foot level instead of drilling down into individual streams. I'm not going to be able to show you nice error bars because it's not a stratified random design, but I can talk about what are the overall patterns that we see across streams in King County. We sampled these sites from 1993 through 2010, so 18 years of data. But remember that this was a monitoring program. It wasn't a single study. So over those 18 years, we had a lot of changes. Some sites were added or dropped. Methods changed, especially the lab analytic methods, giving us lower and lower detection limits over time. Funding waxed and waned, and even the questions that were driving the monitoring seemed to sort of shift over the period of that. These sites were individual grab samples collected 2 to 6 times per year. There's that funding waxing and waning. So these are all instantaneous concentration measurements that I'll be showing today. A lot of people ask about, well, do you have loading rates? And I don't. But from an aquatic organism's perspective, it's that instantaneous concentration that's the most important for what's affecting toxicity. We would really like to have some information on how long the high concentrations persisted for to get at more chronic effects, but we don't. So when I'm talking about acute or chronic toxicity, it's all just coming from these instantaneous measurements. These samples were collected during wet weather conditions when streams were receiving storm flow. We followed basic ecology protocols for that, where we had 24 hours of antecedent dry conditions and then at least a 1/4 inch of rainfall. Now, just around King County, even in that lowland area, there's considerable microclimate variability, and so we can't guarantee that these conditions were all precisely met for every site every time, but this is at least the gist of what we were going for. When we brought the samples back to lab, they were analyzed for 24 different metals total and then filtered for the dissolved fraction on an ICP mass spec. So the first question that we wanted to ask with this data is, did we see any toxic effects? To get at that, first compared our results to the Washington Water Quality Standards for aquatic life. These standards were designed to be protective of about 95% of the aquatic community, and they include both an acute instantaneous or 1 hour standard and a chronic standard. We used the chronic thresholds as well, just seeing if our samples were above them, even though we couldn't say, did it persist for the 4 days to actually qualify as a regulatory chronic effect. The other thing I want to point out is that I'm not going to be asking were these streams in regulatory compliance at the time. Standards have shifted. I'm using today's standards, today's best available science, looking back to ask, were there any problems? So this isn't about were they in or out of compliance. If you're familiar with things like the biotic ligand model, yes, I would have loved to have run that, but we didn't measure dissolved organic carbon or some of the other parameters at that time. Going forward, I would definitely recommend using some of the newer toxicity work, but with the older monitoring program, this is what we have to work with. So as I'd mentioned, these standards protect about 95% or so of the aquatic community. And one thing they don't do a very good job of protecting is salmonids. There's increasing evidence that salmonids can be harmed by metals concentrations at substantially lower concentrations than the water quality standards. And we care a lot about salmon here. So my colleague Janae Colton in our toxicity unit has developed a set of draft screening values, pulling out the salmonid-specific toxicity research and saying what concentrations might harm the salmonids. So that's the second set of criteria that we use to assess toxicity there. And we did find some common toxicity concerns. For the aquatic life standard, mercury was commonly above the chronic standard there. And then for the salmonid screening values, copper, lead, and zinc were pretty widespread. I don't have numbers here because we're dealing with a lot of method detection limit issues, and often, especially for the salmonid screening values, those are below where our laboratory instruments could go. So for zinc, we know that basically every sample in every stream over 18 years was above the salmonid screening values for zinc. For copper, about 30%. Lead was somewhere in the middle. There were just enough indeterminate samples that all I can say is 30 to 100%. So that's why if you want quantitative details, I'll have a few tables in the report that give all of those bits. But what I am confident in saying is that for all of our stormwater managers, these are worth keeping an eye on. They're widespread enough that your stream probably has some issues with these. And as you're thinking about stormwater management and BMPs, if you can remove these, it would be a good thing. We don't need more studies. We know enough that we need some action. All right, so we found high metals concentrations in streams, but was it actually coming from stormwater? We did a baseflow comparison. For a few years during the study, 2001 to 2003, our routine monthly monitoring at these sites also collected samples and analyzed them for metals. We went back and sorted out that data to see which were wet weather and which were dry weather. So we have a baseflow comparison. And we found that for several metals, indeed, total concentrations were higher in stormflow, several toxics and a few others. But what I'm most interested in is the dissolved fraction, because that's what contributes the most to aquatic toxicity. And for those, we've got chromium, copper, nickel, lead, and zinc had both the total and the dissolved fraction higher in stormflow. So yes, the stormwater is bringing in more of these metals in dissolved forms that can harm aquatic life. And so the copper, lead, and zinc that we saw had high concentrations for salmonids are coming in more in stormflow. The third question that I looked at was trends over time. 18 years of data, are things getting better or worse? If anyone wants to geek out over non-parametric statistics that can deal with multiple censoring limits, because we had our lab methods get better and better and better over time, you can talk to me after. I can really talk your ear off about the stats. But the short answer for everyone else in the room is that it's good news. Some toxics decreased. Chromium, copper, nickel, and lead all had decreasing trends over time. Zinc was a little ambiguous, total fraction decrease, dissolved fraction increase, so I need to sort that one out further. Second piece of good news is that hardness increased, calcium and magnesium concentrations. Calcium and magnesium have protective effects on aquatic life. They bind to the receptor sites and they prevent the toxic metals from getting in. So with some of the toxic metals decreasing and the calcium and magnesium increasing, things are getting better overall, especially in terms of that aquatic toxicity. And the last question that I'd taken a look at was trying to tease out pollutant sources. With all of these metals from all of these sites, I was hoping that I could find some patterns in the data. Just taking a fairly naive look at first, some non-dimensional NMDS to see did things cluster. What I had expected to find, spoiler, I didn't, is that I might see a cluster of sites that had similar patterns of what metals they had, say from road runoff, maybe another cluster of sites, different metals coming from industrial sources. Instead, what I found is that each stream was unique. Especially the streams with the highest metal concentration looked nothing like each other. They just had different ones that were high. So getting into that story is going to be a lot more individualistic, stream by stream, and is going to require really bringing in external knowledge for what might be causing these. What I did have a lot more success with, though, was looking for chemical signatures of weathering. All of these metals are found naturally in rocks and in soil, and they get into water through those processes. It's important to remember, though, that weathering is also a human effect. We can accelerate weathering a lot through construction sites, which we've had here since the last century or so, as well as through changes in the stream flow, weathering in more from within the stream channel. And to take a look for weathering, I used iron as a tracer. Iron is naturally present in high enough concentrations that our anthropogenic inputs basically get dwarfed. So what we can do is take a look at metals coming in and ask, are they coming in the same concentration with iron, or are they coming in at a higher concentration than we would expect from a different source that isn't weathering? And what we found is that most metals in most streams were coming in from weathering. The exceptions are interesting, and I'll show you a few in a moment, but overall, weathering is a really major source of these metals. I want to give one caveat with that, is that this iron tracer approach looks at total concentrations, so say total copper versus total iron. And as I'd mentioned before, it's the dissolved fraction that's most important for aquatic toxicity. So even though I'm saying most of these metals are coming in from weathering, there can still be other smaller sources contributing dissolved fraction specifically that this would miss. So I'm not saying weathering is the only source by any stretch. Let's take a look at how this works. I'm going to show you a few graphs where we've got total copper on the y-axis, total iron on the x-axis. Each dot is an individual sample. It's a log-log scale. And most streams look like Ebright Creek here. We've got a nice line where everything clusters pretty tightly. In this case, we can see that copper is coming in just paired with iron, most likely from a weathering source. There were some streams where we saw that same pattern, but with a few exceptions. These samples here, we would expect to have copper concentrations much, much lower than what we found, just based on the amount of iron in those samples. So for those samples, we would say that that's probably a non-weathering source, something else contributing copper that isn't paired with iron. And that's something we can use as a rapid detection method, where as soon as we get the data back from the lab, once we've established what's a typical ratio for these streams, anything that's an order of magnitude above it, like this, we would say something else is going on. Is it something we need to check out as a possible pollutant source in the watershed? And lastly, we had some streams that were weakly or really not at all correlated with iron. So for Fairweather Creek and Mill Creek here, something else is going on. Weathering is not driving the copper inputs in these streams. What else could it be? And for Mill Creek, it turned out to be a really interesting story because I had 6 metals that were basically uncorrelated with iron. Chromium, copper, lead, nickel, vanadium, zinc. What's going on here? As I started looking into the watershed, I can't prove that this was the source, but it's at least a likely culprit. There's an old industrial dump just upstream from our sampling sites. It was Superfund listed for some of these same metals. It's been remediated. these are not really high concentrations of these metals, but the chemical fingerprint shows that they're coming from something other than weathering. This gave me some really good faith in this method that even at these not screamingly high concentrations, we can fingerprint that it's a non-weathering source. So I do think this approach is really useful for starting to understand where the metals are coming from in our streams. So to recap what we found, we did find some common toxicity concerns across many of the streams in King County. Mercury for the chronic aquatic life standards, and then copper, lead, and zinc in high enough concentrations that they could be harming the salmonids. Overall, trends were improving. Some of the toxic metals were decreasing. Hardness was increasing. Both of those are good things. And lastly, weathering seems to be a major source for these metals. Again, just with the caveat, I'm not by any stretch saying that it's the only source. All right, thank you.